Okay, thank you, Jennifer. And thank you, everyone, for attending. Welcome. And today, as Jennifer mentioned, we're going to look at saturation height functions. Basically, as Jennifer said, we're based on the end of the capillary pressure, where I touched very, very briefly on aspects of saturation height, or some of the questions we're on asking about that. And so we, by strong demand, put this together. So what we're going to look at today, I'll do a quick recap of capillary pressure, then a little introduction on saturation heights and the sort of workflows that you might require to do, an overview of some of the functions that might be used, or some of the models, capillary pressure models that might be used in helping to build saturation height functions. And then we'll look at a specific example of quality control process and Leverett-J Foil and Lambda functions in particular on one set of data. So that's what we're going to look at as we go through today. And there's, as Jennifer said, there's quite a lot to get through. This morning, I might have overrun my speaking bit. I'll try and keep it to about 40-45 minutes. It was a little more than that this morning, but hopefully you still find it interesting. So just as a quick recap of capillary pressure, what we looked at last time was that capillary pressure fundamentally is controlled by wettability. So wettability is the is how affinity of fluids or compounds for another compound. So the affinity of one fluid to a surface over and above another fluid, so it could be water in the presence of gas, and water has a strong affinity to the surface, say glass surface, stronger affinity to glass surface than water has to itself, particularly in gas environments. And so it sticks to the surface, and the force that it sticks to that surface can be determined by the interfacial tension between the water and the other fluids. So if we're in a gas environment, water and the gas, and the contact angle that the water sticks to the surface of the water is adhering onto the surface. And that's given, the balance of all the forces is given by this sigma cos theta. So in the presence of oil, generally we're using about a contact angle of about 30. And so we have the interfacial tension between oil and water times the cosine of 30 will give us the force with which water is sticking to the surface. Now, when we come into capillaries, we looked at how if you place a capillary into a fluid, if that fluid is wetting, it will be pulled up the capillary, and depending on the size of the capillary, it will be pulled to different heights. Now, in our reservoir, we don't start with two fluid systems initially. Our reservoir began filled with water. So it's not like the reservoir is pulling water up the reservoir and up the capillaries. They were already filled. But then oil migrates in, and initially oil moves through the biggest pore spaces, depending on the pressure in which it came in, and begins to accumulate at the top of the reservoir. And as it accumulates, you begin to get density. Because of the density difference of the fluids, you begin to get a gravity difference, a gravity segregation, you get a fluid density gradient. And so the pressure difference between the oil and the water begins to build, and the oil begins to push into smaller and smaller capillaries. And at some point, it will overcome particular capillary sizes and push, and it will fill all of the capillaries controlled by that pore throat or any capillary sizes or pore spaces behind the pore throats of that specific size for the pressure of that oil as it gathers. And so what we observe in our reservoir is from the point of free water level, where we've got capillary pressure is 0, we get this increase in the fluid gradient because of the density difference in the fluids. And at the top of the reservoir, we have the highest density difference. So the pressure in the oil can push into smaller and smaller capillaries high up in the reservoir, and low down in the reservoir closer to the free water level, it will only access the larger pores of our system. And this is governed by 2 different equations. So that capillary pressure, or the pressure controlling, controlled by the size of the capillaries, is given by the Young-Laplace equation, 2 sigma cos theta over r, where r is the radius of the capillaries, sigma cos theta, the interfacial tension and contact angle of the fluid pair. Or it's given by this density difference times gravity times the height of the column. So these are the forces governing that. And what this helps us to do, if we understand the capillary pressure, so if we understand what our capillary pressure is, then we can understand a height in our reservoir from a free water level. We can directly correlate it by this equation, understanding the density difference of our fluids. And from any capillary pressure analysis in core, we have a capillary pressure matching to some saturation level. So then we can derive saturation. And that's basically what we're doing in the saturation height modeling. It describes the saturation for a given height, which is equivalent to a given capillary pressure, for the rock quality at that layer height in the reservoir. And because we've got changing quality in our reservoir, depending on the height and different layers and different rock qualities, then we get slightly different saturations. So that's what we're attempting to do. It allows us to then calculate the water saturation, and 1 minus the water saturation is then our hydrocarbons in place. So it allows us to calculate our hydrocarbon in place, our oil volume. Now we have a lot of data, not just from core, we've got the logs. Logs are continuous throughout the system. Core samples, we only tend to have specific intervals. So there's a much greater density of log data, which would be very useful to have maybe to improve the calibrations of. And that's what the core data is attempting to do, to improve the calibration of the log, to get a better understanding and tie log data more directly to the rock that we're looking at, to your reservoir. Because obviously in logs, they have a particular offset or calibration. So in electric logs, you may have a specific A, M, and N that are being used. Or in NMR, you've got a T2 cutoff that might be used. And in the core data, we can segregate all the different controlling factors and allow us to pinpoint what each of those factors might be for given lithologies. So the core capillary pressure is a more direct relationship link between rock quality, capillary pressure, and saturation. So it's a basic concept, and this is what I showed at the end of capillary pressure. What we're attempting to do is we're building up a picture or an image of our reservoir, understanding, looking at these different layers. And in this simplistic case here on the left, we're looking at porosity layers. So we've binned the porosity into different portions. So we've got one which goes from 6 to 10 porosity units. The next one here it would be 10 to 14. Then we've got 14 to 18, where the average, this is denoting the average porosity of that layer. And the largest porosity is from 18 to 22%. And so what we observe, each of those have been measured and show different capillary pressures So that when we're going up the reservoir from our free water level, we're first in a layer of 12% or average at 12% porosity. So we follow the 12% porosity curve. When we go into a new layer, then we then accessing a different capillary pressure curve. And then we go back to the 12% porosity at this layer here, and then into 16% and so on. And that's a simplistic way of looking at what we're attempting to do. And the case on the right here is some alternative data where each of these different stripes in here are a different layer with different rock quality. And so as we go through that, we observe different saturations as we enter into each of those layers. And depending on how finely you've denoted the different layers, how thick each of those layers are, and how well you've defined it, you can get either large layers or very, very small layers. And of course, with log data, the log data is giving you data at specific intervals. And if we have all of that data, we can build up quite a fine layered system. So as we begin to look at the process of saturation height monitoring, we need to look at our core data and we need to consider it. We need to look at quality control of our data. It's very important. If you've got good capillary pressure data, it will probably lead to a good saturation height function or saturation height model. Bad data, if there are errors in your input data, there are going to be errors in your output saturation height model. So poor data will lead to inappropriate or poor saturation height modeling. So first, look through your data, quality control the data, and later I'll go through, as said, just a portion of the sort of quality control that you might perform on this. So you go through the data and then you look at the data. Look at sample selection, look at your reservoir, look at the distribution of porosity in your reservoir, look at the distribution of permeability in the reservoir, and consider, has my core data, is it described, have I got samples from each of the distributions that I'm seeing in my reservoir? Do I see the same distribution in my core data? If I don't, I may need to acquire new data. I may need to set up new tests to acquire data in the missing portions of my model area or missing layers of my reservoir. It's also worth to note that when we're scaling this up, there are going to be uncertainties. We may need to do stress corrections, particularly if you've used mercury injection, or if you're using centrifuge or porous plate without any stress, you will need to correct for the impact of stress. We need to potentially look at clay-bound water corrections, particularly for mercury injection processes. We will need to consider the impact of interfacial tension and contact angle. Particularly if you in the laboratory, we're using often laboratory fluids. They will have a different IFT, or even if you're using a crude oil rather than a live oil, there still may be differences in IFT between that and the reservoir. And also the height of a free water level. We may need to be adjusting the free water level depending on what we're seeing. So there are all of these adjustments to make. And then lastly, or another one on the list here, sample bias. So if we observe that we've got a particular range of porosities or permeabilities that have been missed in our sample selection, then that could bias our data. So we may need to begin to look at weighted functions for our height model rather than just a direct correlation. Or we need to go and acquire additional data for those missing portions. So what we do is we construct a quality controlled capillary pressure database. So we perform rigorous data QC. We eliminate samples we don't believe. We maybe put some tags on other samples to be careful of, so that we can do some sensitivity analysis around using it with or without those questionable samples. Make sure we've got representative distribution of our poroperm, and also bring everything into a common fluid system. You will have capillary pressure from air mercury, you'll have capillary pressure maybe from gas water and oil water, maybe also gas oil. We need to, when we're looking at a specific fluid pair in the reservoir, we need to bring all the capillary pressure data into that fluid pair to begin to perform these models. And we either do it at this stage here and begin to build our fitting functions and our model curves to data at reservoir capillary pressure with the reservoir interfacial tension between the fluids, or we do it to the laboratory data and then convert it afterwards. So you've got to be careful which order you're doing it, because you don't want to either not convert because it was missed, or double convert because you've maybe converted it here and then are converting it again here. So be careful how you're applying the conversion to reservoir capillary for reservoir fluids. But you fit your models, you acquire, if it's the J function, you calculate the J function for all your samples, you obtain calculations of that fit, and begin to apply it into a capillary pressure for the height. Then convert that into reservoir functions if necessary, and then compare your calculated data. So on here, the red is the log saturation direct from the logs. The green is a bulk volume of water calculation. The dark blue underneath is the J saturation. And these blue points are Dean Stark data. And we can see that there's a reasonable correlation to most of these. So there's some portions we're missing what the log is seeing, but it's in general a reasonable correlation. So what functions are out there? I said when we put out the advert for the webinar, I said, you know, a Tamiya, J-function, Skelt-Harrison, which one it works for saturation height modeling? And unfortunately, I'm not going to be able to answer that for you in this here, because every reservoir is different. You will have to go through looking at one of these models, and if that doesn't work, you go on to another model, whatever that might be. And I generally tend to, if I'm in sandstones, I tend to start with a J function. If I'm in chalks, I'll start with the EQR. If I'm in, and I'm working with MICP on carbonate systems, I might start with the Tamiya. But I will start with one and see how it looks, maybe do another one, see how it compares to the first one. But if I get a good match with one, then I have a fairly confident of going ahead with just that one without doing additional work. But you may need to begin to look at different functions. And as we go through this, you'll see that many of the functions are very similar. They're based on very similar parameters. So this is the J. J is basically here's capillary pressure. What we're doing with capillary pressure is we're dividing it by sigma cos theta. Now, we know that sigma cos theta is the controlling fluid aspect of the capillary pressure. So this basically makes capillary pressure independent of fluid type. So it's dimensionless to fluids. We're also then considering the impact of rock quality, permeability divided by porosity, or the root permeability over porosity. So that this is a dimensionless term. It's accounting for rock properties, it's accounting for fluid pair. And so apparently very different capillary pressures could all collapse onto one or fairly unique line, potentially, if you've got a relatively a similar rock type or homogeneous reservoir. Because of what we're going through, I'm probably going to come on and answer some of the questions at the end. So please feel free to ask your questions just now, but I will probably leave them to the end. If there's a specific slide that they refer to, the slide number's down here. Please put the slide number on so that if I need to come back, we can do that as well. So you calculate J based on the capillary pressure for each point that you've measured for every sample. What you can then do is plot all of that data as one data set. As long as they all come from the same rock type, you will see correlation. So they will correlate like this. Saturation is A over J to some power. Now, this can also be termed saturation equals A times J to a negative B. You do that, and then once you've got a correlation here, then for any given permeability and porosity at a known height in my reservoir, from it could be log perm or log porosity and the derived permeability from it, for a given height, and from that height I can calculate the capillary pressure at that height for the fluid density. Then I can calculate saturation. But no, it needs permeability to implement it. So we need to have a good understanding of our permeability porosity correlation. And this is just showing you a few samples, 4 samples here. There's the J function of those samples. What we see is those very different capillary pressures basically align, 3 of them align on together. One sample is different. And that one sample, we now begin to need to ask questions about that sample. Is it different because it's a different rock type? Is it a different because it's an error in laboratory process? Is it different? There are various different reasons. We begin to investigate why it's different. So once you've done that and you're fairly certain of your data, you plot your data like this, you obtain a fit, power fit to the data. Note that where J will not be the y-axis, we're actually inverting this for when we do this for saturation height. We want our saturation to be a function of J, not J a function of saturation, as this is showing, but it basically look very similar, and I'll show you a one later. So we obtain the equation of the curve, and that equation, so this is it inverted, so saturation is this function of J, so 40 times J to this negative power. That then becomes is input, so there's the A, there's lambda, and this is my capillary pressure, or J term, including the permeability over porosity. So now for any given height with a known log porosity and it's a corresponding permeability, I can calculate saturation. And I can then plot that against my log saturation, the log data depth, and see how it matches. Lambda function, so J actually contains rock properties within its within the approach. Lambda function is basically an empirical process of matching capillary pressures and then taking these data. So in this function, what you'll notice, this is very like the Brooks-Corey function, but it's the inversion of Brooks-Corey. So Brooks-Corey says PC is equal to saturation as some factor times saturation to a negative power. What lambda says is we're actually looking for saturation based on capillary pressure. So saturation is some factor divided by capillary pressure to some power, or this can be rearranged saturation is a factor times capillary pressure to a negative power. And so this will be the intercept, and this is the curvature of this single exponential curve that we're applying. So this is how these different, the dotted lines or the lines here are the fitted data based on this. Now you can set this up in Excel. Excel has a solver. You can do this calculation, make a saturation calculation that uses this formula. You can then look at how your calculated saturation compares to the measured saturation. That will be here. To take the square, the sum of the square of all of those differences, the residuals. So this is least squares processing, least squares regression, and try and find the A and lambda that give you the least squares of the sum of the square of the residuals. That will provide you an A and lambda for each individual sample. We then have to then ask the question, what's controlling how A and lambda? Are there reservoir properties that control this intercept and the curvature? And this is how it's then implemented into the reservoir. So A and lambda, and this is capillary pressure as a height. But be careful when using the IFT. So you either do it here or you've done it before. You could have used reservoir capillary pressure here, converted all your laboratory capillary pressure into reservoir capillary pressure, and done all of this process with reservoirs if you know the IFT. So if you've already done it, you don't need it here. So be careful with that. So this is then a graph showing you the correlation of A versus reservoir quality index. And we get a reasonable exponential curve fit for A for those samples. And then this is lambda. So in here, there are probably about 30 or 40 samples that have been measured. And each of those, we've got an A and a lambda for each of individual samples. Each sample has a known RQI, or which is reservoir quality index, 0.0314 times the square root of K over 5. And so we can plot those and get an equation to the curve for this. So then for any RQI, I can now, from that equation, have an A and a lambda, which can then be input into this to give me a saturation at that height if I know porosity and permeability. So the process, determine your A and lambda, then convert your lab to reservoir PC, convert the PC to a height, determine saturation for that height, and then compare your log versus core data. The Tamiya function is basically set up for mercury injection process. We have three parameters here, three variables in the process: G, PD, which is entry pressure, basically, and SB infinity, or S mercury infinity. So the saturation, mercury saturation at infinite pressure. And this is the equation for that, rearranged slightly. So we've got my current pressure, the entry pressure, the current saturation, the saturation at infinite pressure. And that's why mercury injection is good for this, because of the very high pressures that mercury injection is able to obtain. We get much closer, well, can't say much closer to infinity because that's infinite, but we get a long way. And then we have this term here, which is a geometric factor, which is basically describing curvature. And all of these so far are a single exponential curve, which is basically saying we've got generally a Gaussian style, a Gaussian distribution or modality of the pore size in that system. Tamiya is one of the functions where there's a documented look at multimodal systems, so that basically you've got the sum of the different modes, as understanding that each of the modes is a Gaussian fit. So this is the way, one of the process that one of my former colleagues and co-author, Isa Skun, did a lot of work. We looked at many samples from a giant field in the Middle East, of about 1,800 samples. That whole field broke down into basically 6 rock types based on a Winland R32. So R32 is like a mean radius to allow us to, so each of those broke down to set these nice units. And then we can build up saturations from that. The foil function is possibly one of the most simple ones. It's using bulk volume of water. Bulk volume of water is porosity times saturation. So you've already got porosity within the unit. So we say the bulk volume of water is this term here, and you're becoming very familiar with this. So it's A over PC to the power B. So this becomes independent of porosity. So this tends to be more unstable in the transition zones, tends to be better higher up in the reservoir. It tends to be far better when you've got a good homogeneous system and there's not great amount of layering. This is how these 4 curves calculate using bulk volume of water. And then this is then the equation for taking that into a saturation height. So understanding the bulk volume of water, find an A and a B for all of your data, all the capillary pressure data, and then this is the equation for that. This is the conversion for meters here rather than for the PSI units being used. Then we have the EQR function, or equivalent radius function. This is very good for chalks. It was actually designed by Finn Engström. So it sometimes is called the Engström method. It sometimes also gets called the Jensenius method with a slight modification on the Engström. But basically what we're looking at for the EQR, we're determining this entry pressure, trying to find how entry pressure correlates to our capillary pressure compared to the saturation as a function of irreducible saturation. So we have EQR, which is a normalized capillary pressure, normalized against entry, and saturation normalized between 1 and irreducible. We place that on a plot together and we find and determine a polynomial fit. So these are our, say, capillary pressure. What we observe in chalks is a high entry pressure, but then a very rapid depletion of saturation. And that's because chalks often can have quite a unique pore size distribution. High entry pressure, but then unique pore sizes. And so can get to quite low irreducible saturations. This is what this would look like if you tried to do this with a J function. Doesn't work at all. It makes it worse. But by doing the EQR method, all of these samples correlated on a fairly reasonable fit on this polynomial fit. Now you have to be careful with polynomial fits. Basically with all empirical fits, they really only exist within the bounds of what you have that you've fitted. You can't go outside of those boundaries, particularly with polynomials. What you do to get this as a function for, say, integrating with logs is from the core data, get a plot of entry pressure versus porosity and get a correlation of entry pressure to porosity. Also get a correlation of SWI versus porosity. Generally what you'll see maybe is a fairly tight SW regime. And those become then the inputs for calculating EQR. So remember, EQR is entry pressure derived from porosity over the current pressure, which is height in the reservoir, and the saturation is normalized saturation based on SWI. So that then for any height, you can then calculate your saturation. So as just a final process, this is taking you through a series of data, none of the data that you've seen so far, to look at what we're doing as we go through the data. First, you need to set up some form of database and begin to quality control your database. So this is only a portion of it. This isn't everything. This is just some of the capillary pressure data and some of the inputs to that. So I've got permeability, porosity at net confining stress. I've got my RQI and a PL or a pseudo, I should say PLT, not PTL, phi Z, FZI, so some flow zone indicator, and so on. But what you'll notice is there are a number of samples I've shown as outliers. I've got given it, the QF stands for quality flag. So I tend to set up data in three categories. 1 is good, 2 is questionable, and 3, don't use it. So these are data I wouldn't be using. And what I've done is put comments here. It's an outlier as a J, and it's also an outlier from previous stress data. So this is the process that we go through. Here's my stress data on porosity. I've got 6 of 34 samples here. Some of them are showing reasonable curvature. Some of them are not. Some of them are showing some errors. This one may be going into pore collapse. This one is showing some uncertainty. So this may not put them as a quality flag 3 yet, but you begin to say, well, I need to be a bit cautious with this. So I give them a quality flag 2. We then look at permeability. So we correlate water perm to Klinkenberg, the stressed water perm to Klinkenberg, and we see all the samples seem to be behaving well. Then you do KOSWI, you correlate that as well. And we begin to see another breakout of several samples here. And we need to question, what are those samples? Is that another rock type? In which case, is it significant in my reservoir? Do I need to take those data and handle them separately from all the other data? So then, if that's the case, then what I'd have to do is build a model based on these data sets and then a model based on this data set, and find some way of differentiating between those two when it comes to the log process. But what we found is actually when we took those of the samples we were going to use, one of them is different. And so then it becomes the question, well, that's probably actually just an outlier, and remove the data. We don't want to take that forward. And it was actually this data set here was that sample. So there's something significantly wrong. Here is the capillary pressure with a wide spread of data. Those are the same capillary pressure brought onto a J function. We see it's a much tighter fit, much less variance in saturation. Here we've got a variance from 20 to 80, at least around this area here. At the same portion of the apex there, it's only about 20% variance, plus or minus 10%. So much more unique. Then looking at entry pressure. So we calculate entry pressure based on a lambda function where A is an entry pressure, Brooks-Corey. Then we've got some data points here which are uncertain. So there's one high, there are these two here. You've got to question, well, these are the same gradient as the rest of the data. Are these a separate rock type as well? So you begin to question your data and ask, Are they relevant? Is it part of the reservoir? Is it not? Do I remove them? Do some sensitivity analysis? What happens with my data if I use them and take my saturation model with them? What happens when I do my saturation model without them? What's the impact? This is showing you the correlation of building the foil and the lambda function. So foil, remember, was the bulk volume of water, A times the bulk volume of water, times capillary pressure to some power. And I haven't shown the factor and the exponent here, but basically we're getting a good match in the foil function and a good match to this sample in lambda function. Here's one that's not quite such a good match. It's still reasonable, but there's some variance in there. So it's not quite as good as the previous sample. So if it becomes too great, and you can use statistical analysis to look at that, then we begin to question whether this should be used or not. And you give it a quality flag, maybe 2 or 3, depending on how poor the shape is. And after we've done all of that, we removed all of the samples, then we go ahead with the samples that we're still believing. Now this is how in the lambda function, after I had obtained A and lambda for all of these samples, about 35 samples in total, this is how A correlates to RQI. You can see we've got, apart from 1, maybe 2 outliers, a very unique fit with a power law fit. So then for any RQI from my log, so if I got porosity from the log, calculate my permeability model from that log porosity, so then I can then calculate RQI. That allows me to calculate A. From this plot here, it then also allows me to calculate a lambda. And once I've got A and lambda, I can then carry that through those previous equations into a height above free water level, and then into saturation from that height, or for the capillary pressure at that height. What I'm doing here with the lambda, I'm showing a P50 as the average fit through lambda, and then a P10 and P90, so that I can begin to look at statistical analysis of the variance of the impact of the variance in lambda of the system. So I can look at the average of the system, and then look at some bounding properties. If I look at the bulk volume of water and how that correlates, because bulk volume of water it incorporates porosity, we're not normally needing to do any additional correlations, but this is just showing you the spread of data. And what you can see is that it's not really a great correlation. It works because you've brought porosity in, and it will work if you've got a fairly homogeneous system. But it actually correlates far better to permeability, or if I were to use RQI, to RQI. So saturation height models always work best when you bring permeability into the equation, if you've got a good understanding of how your permeability correlates to porosity. So once we've done all of that, I build up my saturation based on either my J function, so correlate it. So from my log data, I've got a known log porosity. I've got then a permeability model. I can then calculate RQI, or I can calculate root K over phi to plug into the J function. I know where my free water level is, or I think I know where it is. And I begin to build up for the given height above free water level, the saturation based on the J function, on my lambda, and on the bulk volume of water. And this is how they compare. And I've got pretty reasonable comparison. And at the peak points here, you're getting good correlation to those peaks. The lambda, not so good. It's generally going through the middle of these reasonable when you're close to SWI, but I'm not quite getting these high peaks here. And the bulk volume of water it's too low. almost everywhere it's a little skewed. So capillary pressure behavior depends on largely permeability is a strongly controlling factor, but because radius, pore throat radius also controls permeability, which is a controlling factor in capillary pressure. Porosity plays some role, but it's probably more minor than permeability. Porosity-based functions tend to be a little compromised. You tend to require permeability. So functions which include permeability often have a better chance of obtaining a better match. And then we need to compare our data. So generally begin to look at how it correlates. Do you have random variation? In which case it's probably basically just variation in rock typing. So that's where building, say, a P10, P50, P90 allows you to look at the variation and make sure you're capturing that within your data set. Or if there's a systematic difference, so like in the bulk volume of water, in this case, where it's always too low, either it's the wrong model, we need to use a different model, or there's some other uncertainty, something, say IFT or my free water level is incorrect, so we begin to question other properties. So in summary, saturation height models from core PC can offer advantages over log-derived saturations, because of uncertainties in the log offsets. Core PC provides a direct link between our rock quality and the capillary pressure behavior. As long as sample selection has been good, we've got representative material that depending on the different tests and corrections you've made to those, and ensuring that we've done all the corrections that we need to make, so sort of correcting for stress or interfacial tension, etc. Most saturation height models will require permeability, and most importantly, you do have to do quality control, rigorous quality control of your input data. So it's that old adage, bad input, bad output. So I want to thank you for your attention today, and we will take some of the questions now. And I did this afternoon in just about the same time as I did this morning. So we've got some time left for questions though. So somebody has asked, anonymous has asked, difference between wettability and buoyancy. Buoyancy is basically about the fluids, and it's how the fluids separate out so that the density difference between the fluids. Wettability is about how those fluids then stick to a surface. So buoyancy is basically in a body of fluid, not to do with surfaces. Bulgao says, so bottom line is these are empirical, so we need to be patient and test. Yes, Bull, that's a very pertinent point. They aren't then, so the Young Laplace is potentially more physical. So how radius correlates to interfacial tensions, etc. But these correlations are empirical because there's no direct link. I said this in capillary pressure. There's no direct link between capillary pressure and saturation. If you had a unique capillary that was filled with a fluid and were able to match or slightly go over the pressure, the capillary pressure of that tube, you would displace the whole capillary. We only get this distribution because we have a distribution of different capillary sizes. Tet says, how can we determine a selected method is a good choice or not? Well, that's so that's going through the process. I don't know if you asked this before we really came to the end. Basically, you perform your saturation height, you compare it to your other data, and you begin to ask the questions. Well, if they are the same or very similar, then you've got say more confidence in the data. If they're different, you begin to either use a different method and see if you can get a better output from a different method, or you begin to question the different data and the different inputs and the other properties that are being input into upscaling your data. Anonymous has said, in case of bias sampling, you said either new coring or weighted functions. What do you mean by weighted functions? So if you've got data here and another set of data which has is much more distributed. So if 50% of my core of my reservoir is 10% porosity, and only 10% of my reservoir is 15% porosity, well, it would be wrong to have 50% of my data in the 15% porosity, which is the better porosity, because most of my reservoir is elsewhere. But if we build a saturation height function based on that skewed data set, then we introduce skew into our data. So what we have to do is basically downgrade the 15% and put more emphasis into the 10% data. So we begin to weight the functions. So this is the thing about curve fitting, because we're getting empirical fits. If we've got a curve like this, you could put a straight line through a curve and get a least square fit. But if you put more weight, that's because everywhere has the same weight. But if you put less weight at the ends and more weight into the curvature, or to particular points of the curvature, the mathematics of that force it into a curve rather than just a straight line. So it needs some thought about how, if you're going to weight, you then have to begin to think about how will you weight it, because you could introduce skew and uncertainty from your weighting method. Boaz then asked another question. Got a general question in your experience, or in Boaz's experience, especially working with some legacy lab data. It's unfortunate that we often see insufficient maximum pressure from lab testing to cover the entire column height. Any general advice on that? Extrapolation and test, compare with other data sources, log, Dean Stark, etc. Yes, so one of the things that I have done is extrapolating data. So using something like a Brooks-Corey or some of these models, Tamiya, to extend if you've got good confidence in the curves going so far, extending it beyond that. Also, with the added of, say, mercury injection, which goes to higher pressures, and correlating mercury injection data with capillary pressure, with porous plate or centrifuge, as long as you've done the correct fluid pairing, make sure that you maybe put them all into a J space, so that they're all in dimensionless fluid. And comparing against logs and Dean Stark. So comparing with other data is always important in this process to ensure that you've got a robust model. And then secondly, regarding Lambda, this is the next question, regarding Lambda Brooke-Corey model, I've seen papers making attempts to connect Lambda parameters to rel-perm curves as say Corey exponents. Have you ever seen that approach work in real data sets? I haven't. I think what I do find is that so going to my previous rel-perm webinar as well, is I looked at the impact of heterogeneity on sample data, and that non-single exponential curvature in rel-perm, it's not always, but often it comes from either heterogeneous samples or very high viscosity ratios where you no longer have Buckley-Leverett conditions. And but I've never tried to myself look at this correlation. I know, so Brooke Corey already had a model of relating capillary pressure to relative permeability, the curvature. It's interesting though, but I've not done it myself. It might be interesting to if I had enough data to consider it at some point. Thank you for that question. PC as a as a function of saturation for J function. Is it the same like imbibition line? I think what, yeah, what I've been discussing today was basically just drainage. Now we have imbibition as well. What I didn't touch on, mainly for time, is so if you have reasonable matches further up and poor matches below, it could indicate some uncertainty in, or say, oil-water contacts. That might come from water influx or from paleo contacts, in which case you will be needing to use an imbibition capillary pressure. So I was only looking at drainage here, but you may also need to use an imbibition process. Now, J function is really only converting capillary pressure into and dividing by the functional fluid group. So the IFT cos theta. So we need to be careful, but generally there is the potential that you can use imbibition, and I've done it a lot for as an input for relative permeability, is converted capillary pressure into J functions to enable to correlate different samples and capillary pressures. You need to be careful because imbibition, the capillary pressure is negative, and you need to sort of convert it into more positive numbers and then convert it back. But it can be done. What time are we? Okay, just a couple of minutes over. How many more questions do we have? And do we have time, do you think, Jennifer?
We have 13 more questions. A few of them are comments. We could run for a few minutes over if everybody would like to stay on. If not, they could maybe drop off, or it's up to you if you want to get back by email.
Yeah, okay, I'll go down and see how time is going. Okay, how to make the difference between entry pressure and conformance or closure correction. So this is a question about mercury injection. And it's a good question because at the start of mercury injection, really that's maybe a question for the capillary pressure last time. But at the start of a mercury injection, you get small deformation of mercury around the sample into the surfaces that's not really injection into the sample. That's conformance. And at some point that stops. You get no more, well, sometimes it stops. It can sometimes be difficult to actually define where it really happens. But that's conformance. The next point you get any injection in, that's entry pressure. So sometimes entry pressure is equal to conformance pressure, but sometimes you get some small conformance, then there's a large period of no injection, but a lot higher pressure, and then you get entry pressure. So they can be different, they can be the same. And you'd need to go back to your raw data and look at them both to check. Jones has said, should mercury injection data be corrected for SWIR as well as clay corrected? Should MICP irreducible water correction be made using surface area? Yes, that's a very good question. So this, with mercury injection, there are many things that could impact those data. One of them is the laboratory process. I've been advising for a number of years that laboratories should measure helium properties, helium pore volume of the sample that they're measuring mercury in. It sort of got neglected for a while. Maybe more laboratories are doing it again now, but we should have a helium pore volume as well as a mercury pore volume, because the assumption often is that mercury fills the whole space, and sometimes that's not the case, particularly where you've got high clay content present, so that you will need to do clay correction. You may need to do an SWI correction, because particularly if it's been based on mercury pore volume rather than helium pore volume. So those may need to be made. Should that be made based on surface area? I think that becomes dependent on the clay content as well. One of the problems with mercury is that you can begin to collapse the clays, which is then changing the surface area. So it becomes quite a difficult process, and I'm presuming that you're thinking about surface area there as something like the isotherms, the thermal absorption, say using methane or rather than nitrogen to look at surface difference, BET of surface areas, etc. But yeah, you may need to do that. Sometimes you may not. So these work perfectly without any problems in clean sands. I mentioned that last time. But when you begin to get clays present, it introduces a lot of potential uncertainty. Farouk says, how to ensure that the selection of core plugs does not bias, such as choosing intact plugs and the subsequent core analysis. Farouk, I would advise you to go back to some of my earlier webinars where we were looking at things like sample selection. Sample selection is a very important process. It's important to get representative samples that cover the range and the dispersion of properties that we observe in our reservoir. But it's also important to know that the samples we're using, as you say, choosing intact plugs, because those imperfections can create uncertainties in the data. So it becomes very important. Bo says, great talk. Thanks, Jules. Okay, thank you, Bo. I hope it was interesting for people, and that's what Peter's saying as well. Many thanks for sharing, most interesting. Mutaba says, will the video and presentation file be available? Yes, speak to Jennifer or email Jennifer if you want a copy of the video and or presentation pack. The presentation will be sent as a PDF. Ugur says, do you recommend getting irreducible saturation? I think for time, I think we probably need to make this the last question. What I'll do is we'll get back to any questions that haven't been answered individually. But Ugur says, do you recommend getting irreducible saturation from MICP data? Because quite high pressure, up to 60,000 PSI is applied, and this is not realistic for any reservoir when converted to reservoir PC. It's not realistic. However, one of the issues, or one of the things with I think I discussed this in the capillary pressure talk, was that we are limited in the reservoir. We're limited by the height of the column, and so the saturation that we get from that is limited by the forces or the fluid gradient at the top of the column, and that becomes SW. Or SW, is that SWIR? Because what if your whole reservoir is in transition? Then at the top of the reservoir, you're still in transition. You wouldn't say, if your capillary pressure curve was still like this, you wouldn't say that that was irreducible. So what is irreducible? And that I did question that a little, or brought that into the forethought of what we call irreducible is a function of either our reservoir height and the limits of the physics of the system, the mechanics of it, or it's a limit of what the laboratory can apply. And if we were able to apply, so 60,000 PSI is about 11 kilometers of an oil column. We can't apply that. What it does do, though, is it allows us to go beyond what the reservoir is and look at what's happening in the smaller space. Now, that small space is not probably pertinent to the oil and mobile hydrocarbons, but it is important to what's happening with the water, because the water will still be able to flow through that space. And so particularly for spontaneous imbibition, where water flows along film flow, I didn't discuss that in the REL perm, but you get film flow. So if we consider wettability and spontaneous imbibition, how does water get pulled so far into the system without any pressure? Well, it flows along in that very small space. So it is important. And the mercury injection is very useful because it takes us beyond that, or below what might be called as irreducible in say an oil water case or a gas water case, and describes the fuller pore size distribution. It still doesn't go far enough because the mercury is so large it can't get into some of the nanospace or the sub micron space. So there's a big question of whether of how important that is. What we do need to be careful of, though, is how we use those data, and just comparing the data from mercury, compare it with the gas water, compare it with oil water, and make sure that they all are consistent. And where we have inconsistencies, we need to take even more care. So it can be very useful data. Okay, so thank you everyone for your attention today. Thank you for the questions, some interesting questions there. Sorry for those who I've not been able to get onto, but please come back and see some of our later webinars. And I'll be in touch for these later questions.
Perfect, thank you, Jules. And just a quick thank you for everybody for joining us. I'll make this one quick, but yeah, as Jules said, just drop us an email with any more follow-up questions, and he will get back to you with the questions we have missed today. Sorry, we have run over slightly, but there was a lot to go through. Hopefully you found it all very interesting. Just looking forward to what we've got coming up very quickly. If Jules goes to the next slide quickly. Justin Green is back in a couple of weeks on the 12th of November. He'll be bringing us acid stimulation, a laboratory perspective, and Jules is then back on the 26th of November with the next topic, heavy oil and unconsolidated core. We will be releasing the registration details and information on our Premier Corex, LinkedIn and social pages next week. So keep an eye on there while you're there. It'd be great if you could give us a quick follow as well. We do appreciate it, and you'll be able to keep updated on our future sessions as well. Okay, I think we'll end it there because we are nearly 15 minutes over now, but thank you everybody for hanging on. Thank you to Jules, and yeah, hopefully we'll see you at future sessions. Thanks everyone.